Okay, all right. Well, my name is Lupsasca. I'm a professor at Vanderbilt University, which is in Nashville, Tennessee. This was quite the trip, but thank you very much for the invitation to be here. It's lovely to be in Vienna and to meet so many great European physicists. So today I want to tell you about the black hole photon ring, which hopefully some of you have heard about, and I know perhaps many of you, but I'm not going to assume that you have. And so my goal today is to tell you what this is, what's interesting about it, and why you should care, and what we're going to learn about it. Okay, so I like to start talks on the subject with this video, which I haven't made. It's been produced by collating actual data from all these experiments listed at the bottom. So everything you're seeing in this movie is a real image. This isn't simulated or anything. So you point your telescope to the sky towards the galaxy Virgo, towards the Virgo constellation, and you start to zoom in. And there's this very distant galaxy called M87, which is 50 million light years away. And it has this jet, which stretches over extremely long distances and has been observed for over a century now. People, when they first saw it in the early 20th century, thought maybe it was aliens. They didn't know what it was at first. And today we think, well, we know that this jet has at its base a black hole, which the Event Horizon Telescope finally imaged in 2019. And I like to show this video because the press release where the image was first unveiled, the first two questions by journalists were, oh, great success, but it's a little blurry. And I think when you see how much you have to zoom in to get this image, it really puts things into perspective. So this is an extraordinary technological achievement, but it is blurry, and we're not done. So now that we know that this experiment works and it's possible, it's clear that we're just going to be doing better, and that's part of what I want to talk about today. All right, so this is what we've seen so far, but we can ask, of course, as our technology improves, what do we expect to see in the future when the resolution that we can achieve improves? And so instead of this blurry donut of light, we think that the actual source on the sky, if you could see it with perfect resolution, would look something like this. And Luciano yesterday described this framework, general relativistic magnetohydrodynamics, which is a complicated theory that describes how matter can flow onto a black hole, and then we can ray trace movies of these simulated accretion flows, and we can get millions and millions of images. And the thing that's striking about those, I think, 60 million images that Luciano mentioned, that you can look at any one of them, and a lot of the details in the images can change. So as you vary the R-high parameter that Luciano mentioned, so the electron heating model and the details of the accretion flow, there's a lot of knobs you can turn. But at the end of the day, you look at the image, and the thing that stares at you straight in the face is this sharp ring of light, which is what we call the photon ring. And so if you're a physicist, this should be a little bit surprising to you. How is it that you can vary all these conditions and still get the same, roughly, image structure? And so the reason, my key point is that, okay, the contrast is a little off, but there's some accretion flow that's falling onto a black hole, and the details of that depend on whatever's around the black hole. We can't predict that from first principles. You just have to look at what's around the black hole. But given some kind of source, some hot plasma radiating light around the black hole, this photon ring will generically be present because it consists of mirror images of the stuff around the black hole that's shining light. And as long as the black hole is there, the characteristic lensing behavior that's created by orbiting light will always produce this lens feature of a ring with properties that encode the space-time geometry around the black hole. So it's the part of the image that belongs to the black hole itself, rather than the circulating plasma around it. And by measuring it, you can actually learn something directly about the space-time geometry, which is what we're very excited to do in the next decade. Okay, so I want to now explain in a little bit more detail. I have a short amount of time, so this will be somewhat telegraphic, but I want to show you the key points in the derivation of this phenomenon. So the story really begins with the photon shell, which is this region of space-time around the black hole. Here I'm showing a Kerr black hole, in which gravity is so strong that light can be pulled into spherical orbits. So this is the event horizon. Here I'm showing a curved black hole of spin 94% of the maximum. And of course, if some photon falls into the event horizon, it can never come back out. That's the definition of the black hole. But outside of the horizon, this was perhaps a little bit less appreciated until more recently. There's this region that we call the photon shell, in which gravity is so strong that light can be stuck on these orbits that are at fixed Bohr-Lindquist radius. This is a coordinate-dependent statement. In fact, the definition of the Bohr-Lindquist radius is that the spherical orbits are at fixed radius. So I'm going to assume these coordinates for the purpose of this discussion. And that doesn't mean that any light that enters this region is captured on closed orbits. It's possible to cross through in any direction, but it is possible for light to stay stuck on one of these shells. And in fact, it's very hard to arrange for this. So if you're at a given radius and you want to load a photon onto an orbital shell at that radius, you have to aim perfectly well. You have to aim your flashlight straight up or straight down to make sure that the photon doesn't fall in or escape. Okay, so if you have a Schwarzschild black hole with an event horizon radius of 2m, it turns out that this shell is actually a single sphere, the photon sphere at r equals 3m. And that case is a little bit degenerate, but as you spin up the black hole, this photon sphere thickens into a shell. And as you approach maximal spin, the horizon shrinks all the way down to r equals m, and the photon shell thickens from m to 4m. So here we're approaching that case. Now, the key point for the discussion today is to notice that these orbits, they're generically not periodic or closed, because the motion in the theta direction, the libration, the polar libration, has a frequency which is not a rational multiple of the azimuthal winding. And so instead of nice closed orbits that repeat themselves, you get this kind of ergodic behavior on the sphere. And Leo Stein, on his blog, has a very cool 3D Java applet where you can actually visualize in 3D real time these orbits. It's very fun to play with. And they look something like this. And for the purpose of this discussion, I want to define the notion of an orbit of a photon to be a bounce from the bottom to the top and back. Okay, so full polar libration, a full periodic oscillation in the theta direction. That's what I'm going to call an orbit throughout this discussion. And I think in this field in general, this has become quite conventional. And in particular, that means that a half orbit is a motion from the bottom to the top, or equivalently from the top to the bottom. Okay? Now, I want to introduce 4 parameters that are intrinsically defined by the space-time geometry around the black hole, called delta, tau, gamma, and mu, that completely turn out to characterize the behavior of light in this photon shell and turn out to be relevant for understanding the image of the photon ray. So what are these parameters? I hope that the definition is quite clear, but if not, please ask me now. So as a photon does one bounce, a half orbit from the bottom to the top, it winds some amount delta phi around the black hole. And that parameter we call delta. And so delta, like all the other parameters, is a function only of the black hole mass and its spin and the orbital radius within the photon shell. That's all it depends on. And you can obtain explicit analytic expressions for all these parameters in terms of these 3 parameters. So that's delta. Tau is just the time lapse incurred per half orbit. So how long does it take for such a bounce to occur? And every bounce takes the same amount of time and rotates by the same amount. And again, this is a coordinate-dependent statement. Here, the time is the Bohr-Lindquist time, which asymptotes to our time as an observer far away, which is why it's going to be relevant for describing images. And then the last one I want to explain on this plot is that you see there is only one radius at which photons are actually free to fully explore an entire sphere. And that is the radius of this white shell, which is the photon sphere that you get in Schwarzschild when the shell reduces to a sphere. And this white sphere is defined by the property that the bound photons on it have 0 spin angular momentum relative to the axis of rotation of the black hole. And 0 angular momentum is required to be able to pass over the poles. On the other hand, orbits, bound photons that lie within the sphere are prograde and have positive spin angular momentum, and photons that are outside of the sphere are retrograde and have negative spin angular momentum. They're counter-rotating with the black hole. And so at the edges, you have circular equatorial orbits. The prograde circular equatorial orbit is the innermost part of the photon shell, and the outermost edge is the retrograde circular equatorial orbit. And for radii in between, the photons bounce up and down between some angle theta max and pi minus theta max. And so mu is just the inclination of an orbit. Again, it depends on the black hole parameters and the orbital radius. But it's a signed inclination in the sense that it's positive in here and negative in here to account for the momentum. And so mu is equal to +1 here because theta max is pi over 2. Mu is 0 here because theta max is also 0. And mu is -1 here because, again, theta max is pi over 2, but now we have retrograde orbits. So mu is a parameter for these orbits, for these radii in the photon shell that always goes from +1 through 0 to -1 as monotonically decreasing. Okay, any questions about delta, tau, mu, or is it clear what I'm talking about? I see happy nods. All right, and now the last one I want to introduce is gamma. And gamma is the Lyapunov exponent that describes the orbital instability of these photons. So like I said, suppose you're here. If you want to load a photon onto an orbital shell, you have to aim it perfectly onto the shell with your flashlight. But if you're a little bit off, so say you push your flashlight off to the side a little bit, and there's some initial displacement delta R naught from the orbital shell. Well, light hates being trapped. These orbits are unstable. And so what's going to happen is that the photon is actually going to zoom off. It's going to very rapidly escape. And by studying the equation of geodesic deviation, you can show that this radial deviation will grow exponentially fast in the number of half orbits. So every bounce, every half orbit, the photon is going to move exponentially far according to this relation. And the exponent that's controlling this exponential growth is gamma. And again, this can be written down explicitly in terms of the mass, spin, and orbital radius. Okay, so I've defined these quantities, these geometric quantities that describe the flow of geodesics in this photon shell. And now I want to connect this back to images, the stuff that we see and care about for observations. So to do that, I need to introduce one more concept, which is that of an observer's image plane. And Bardeen in '73 did that. So the way to think about it is that whenever you look at a black hole, you can define a line of sight to the center of the black hole in a way that can be made precise in GR. So you have a line of sight to the black hole, and then you look at the plane perpendicular to the line of sight, and you project the spin axis of the black hole onto that plane, and that defines this vertical axis beta. And then you take the perpendicular axis, and that defines alpha, and you can make this precise with equations, but that's all that's happening here. And so now that you have an image plane, you can ask, if I aim my flashlight towards the black hole, if I shoot a photon towards it, what happens to it? And there's two behaviors that you expect. So one is if you aim your flashlight directly towards the black hole, you aim near the origin, well, then you expect the photon to come in from far away and go into the black hole, and that's what happens. It gets trapped. On the other hand, if you aim very far off to the side, the photon will sort of come in, will feel some pull from the black hole, it'll be deflected a little bit, swerve, and then go back out to infinity. So what that means is that on your image plane, there's clearly a region of photon capture near the origin. That's where if you shoot photons, they fall into the event horizon. But if you aim very far away from the black hole, there's a region of photon escape where they go back out to infinity. And the question is, what is the boundary that delineates between those two behaviors? And Bardeen derived this analytically. We call this the critical curve, which I've shown here in red. And so this is a mathematical curve on your image plane, which is the boundary between photon capture and photon escape. And now, for those of you who've been following, the question is, what happens if you aim a photon exactly on this boundary? So if you aim inside, the photon falls in. If you aim outside, it goes back out to infinity. But what happens at the boundary? Very good. So if you aim exactly on this critical curve, the photon can neither be captured nor can it escape. And so what happens is that it comes in from infinity but gets loaded onto one of these orbital shells. And in fact, the way this works is that depending on where around this curve you aim your photon, that will change which orbital radius in the photon shell it gets loaded onto. And I want you to pause for a second and think about how weird this is. Because if you have a star and you look at an image of a star, then as you look around the image plane, you're also looking around the star, the azimuthal angle in the geometry. But here, what I'm telling you is that you have a black hole spacetime, and as you look around the angle in the image, you're really looking not around the black hole in phi, but actually closer or farther away in r, in radius. And that is really the warped nature of spacetime in your face. Okay. And this critical curve, again, is known analytically, and it depends only on the black hole parameters, the mass, the spin, and also the observer inclination. Okay. Any question about this? Yes?
Sure, it's shifted to the right due to the spin of the black hole, the circle?
Yeah, that's true. So again, the center of this coordinate system is a little bit artificial. You have to define what you mean by the center of the black hole, and that changes as it spins up. But it's true that as you increase the black hole spin, this curve will tend to shift relative to the center. And the reason is that photons that are prograde tend to get slingshot as they co-rotate with the black hole, whereas photons that are retrograde have to kind of swim against the current. There's frame dragging. And so that means that the photons that are co-rotating can come closer to the axis of spin. It's a subtle effect. D is my next point. Very, very good, thank you. So in the real world, it's actually impossible to aim perfectly well onto this mathematical curve because it's infinitely thin. So you'd have to have infinite precision. And this is like a separate discussion. I was reminded by this from Luciano's talk. At some point, if you want a photon to orbit for a really long time, the actual wavelength of the photon will start to matter. And because real photons have finite wavelength, it's impossible to aim them perfectly well and get them stuck forever on these orbital shells. So this isn't immediately obviously relevant to imaging. And in fact, to understand the photon ring that dominates black hole images, we have to think not about the perfectly bound photons, but the nearly bound ones. So the ones that are aimed very close to this critical curve, but like not exactly on it, because that never really happens in the real world. And so the question is, what happens if you aim a photon at a very small perpendicular distance d from this critical curve? So if d is very small, then, so you know that if you aim on the critical curve, the photon comes in and goes around forever. And what happens is that if you aim a little bit off to the side, the photon will still come in, skirt the bound orbit where it would have been trapped if d had been 0, but eventually will fly away. And if d is slightly positive, it must come back out. So the photon will come in, wind around a bunch of times, and then escape back out to infinity. And if d is slightly negative, then it will come in, skirt the orbit where it would have been bound if d had been 0, possibly for a long time, but eventually fall in, because by definition, that's what happens depending on the sign of d. Okay? And based on this previous equation, you expect that in order for a photon to do one additional turn, so you say, okay, I want a photon that does 10 turns, how close do I have to get? And the answer is you expect that d has to be exponentially small in order to get an additional turn. And that is indeed what happens. So to put this together now, we're going to discuss finally black hole lensing around a rotating curved black hole. And the key point that I want to make from this discussion is that because a consequence of this, you can prove this mathematically, is that any two spatial points in a black hole spacetime are actually connected by infinitely many light rays. There are infinitely many null geodesics or light paths that connect any two spatial positions. And I'm going to explain this very quickly in the simplest examples, in the simplest example possible, which is this one here. And it's a bit of a cheat because the full problem is a lot more complicated, but in this simple story where you have an equatorial disk and you look down on it from the spin axis of the black hole, that's a special configuration. I put my observer on the rotation axis of the black hole looking down at it. This is the face-on configuration. And there's an equatorial disk. In that case, the equations that describe the pattern of lensing become extremely simple, and I can explain them to you in this one slide. So what's going on here? This is my one scary slide. So on the right-hand side, I have the setup that I've just talked about. So there's an equatorial disk, and my observer is on the spin axis. And if I have a point source in the disk, I expect to see many images of this point source. And in particular, there'll be an n equals 0 photon, which comes directly at me. That's the direct image that I would expect to see in the absence of a black hole. But because there's a black hole, there's also an n equals 1 photon, which is initially shot away from me, that goes downwards, but then gets captured by the black hole's pull, does one extra half orbit around the black hole, that's why it's called n equals 1, and then gets sent back towards me. And yesterday, Luciano showed some images in which the black hole image was dominated by the counterjet, the light that is shot away from you. And if that's surprising to you, hopefully this can be helpful to illuminate what's going on, which is that the light that's shot away actually gets lensed back towards you, and that in certain situations, that can be the dominant source. Okay, and then you also expect some n equals 2 image from light that does 2 half orbits or circumnavigates the black hole a full orbit before coming back to you, and so on and so forth. And the key point here is that whatever the direct image is, whatever the n equals 0 image is, I can't predict that from general relativity. That's just showing you whatever is in the disk around the black hole. You have to know about the astrophysics of the source. But in the large n regime, you can solve the geodesic equation and curve exactly, and then you can expand it in 1 over n, where n is the orbit number. And you can show that there's a very simple relation between one image and the next, which is purely predicted by the geometry of the spacetime and how the black hole lens is like. And so this behavior here is illustrated by this panel here. So suppose that the mth image that you see of the disk is this color wheel. This is totally artificial, but it's just to illustrate the point. The black curve here is the critical curve, the set of directions where light gets stuck on orbit, so the image of the photon shell. Well, if this is the mth image, then the m plus 1th image, at least the large m, can be completely described by these equations, and there's 3 effects. So the first effect is this squeezing towards the critical curve, or demagnification. And the demagnification factor is exactly e to the minus gamma. So if you'd seen an image of your source at some position dn, the next image of the source from a photon that does an additional turn has to be exponentially closer, exactly by an amount e to the minus gamma, because you have to aim exponentially better in order to get the photon to stick around for 1 extra half orbit. And the squeezing effect is exactly e to the minus pi for a Schwarzschild black hole. So that's about 5%. And for a rapidly spinning black hole, the magnification factor increases, so you have less squeezing until it's about 10% for a high spin black hole. Okay, so that's effect number 1. Effect number 2 is that the image rotates. And you can see that here, which is that if the n equals k, k image comes from the right, then the k plus 1th image will go around the black hole and come to you from the other side, from the left. And if you think about what that means for every point around the ring, it means that it rotates by exactly pi degrees, or 180 degrees for a Schwarzschild black hole. And as you spin up the black hole, because there's frame dragging, the photons wind around more. And at maximal spin, you can get almost exactly 3/4 of a turn. So it's between half a turn and 3/4 of a turn. And then lastly, there's a time delay, tau, which is how much extra time it takes for the photon to do an extra orbit. And this number is about 16 m, independently of spin, roughly. So for M87, where m has the light crossing time m is about 9 hours, this would be about 6 days. So if you look at M87, you expect to see light echoes on a time scale of about 6 days. For Sagittarius A star, which is 2,000 times smaller, the light crossing time is about 20 seconds, and so this time is a few minutes. Okay, so that's black hole lensing in a nutshell. Now I have a cool video to put everything that I've told you together. So what happens when you look at a black hole? Well, there's going to be some hot stuff around it that shines photons, shines light. And so most of this light is weakly lensed. It's deflected a little bit, but it comes to you and shows you an image of the accretion flow onto the black hole. It just shows you what's around the black hole. That's not GR, that's astrophysics. But some of the light will be aimed just right in order to skirt the photon shell for 1/2 orbit. But because it has to sort of do this U-turn around the black hole, it gets lensed into this ring-like shape that hugs the critical curve. And it's possible, of course, for light to be aimed exponentially better and do 2 half turns and 3 half turns and so forth. And those additional mirror images of the source get lensed into exponentially narrower rings. And because this is electromagnetism, everything linearly superposes, so the full image is just the sum of all these layers. So the totality of what you see is something like this, where you have an image of the accretion flow onto the black hole. That's this background stuff here. And superimposed on top of it, you have the signature stamp of the black hole and its strong gravity, which is this photon ring that hugs the critical curve, whose shape is set by the parameters of the black hole. So roughly, you can put a ruler across this ring, and that lets you measure the size of the black hole or its mass. And I won't have time to get into it today, but there are ways to extract the spin too. It's just a more subtle effect. Okay, so this is my summary slide for the theory. It's a prediction of general relativity that within a black hole image, you ought to see a thin photon ring, which is itself composed of a stack of many subrings. And these subrings are self-similar because they're just mirror images of the same stuff around the black hole that are produced by photons that execute an increasing number n of half orbits around the black hole. And so you can label the subrings within the photon ring by their orbital number. And the structure of the photon ring is governed by the lensing behavior of a curved black hole, and is completely characterized by these 3 measurable photon ring parameters, gamma, delta, and tau, that control, respectively, the demagnification, rotation, and time delay of successive images. I showed you the simplest case, but in the more generic configuration, this is still morally true, although the equations are more complicated. And lastly, these photon subrings, they converge to a specific shape that is predicted by the Kerr geometry, Bardeen's critical curve. And it is now a target for future observations of black holes to resolve this photon ring around the black holes M87 and Sagittarius A star. So before I describe this effort, let me say a couple of words about where we are today experimentally. So everything I've told you today is predicted by general relativity, but hasn't been observed yet or tested in the real world. The best that we've done so far is to confirm this in state-of-the-art numerical simulations. So this is a ray-traced, time-averaged image of a super fancy GRMHD simulation that George Wong made. And you can take cross-sections of this intensity profile, so a horizontal and a vertical cut. Those are shown in red and blue here. And you can see these spikes in the intensity, which correspond to the photon ring. And then in these panels, we zoom in on these spikes to see what's happening to the intensity in the image. And George actually decomposed the total intensity that you see into contributions that come from photons that did a different number of turns. And so you can see that there's this shoulder, the background image, that's the n=0 image of the accretion flow. And then superimposed on top of this, there's a squeezed, demagnified n=1 image of it. And then there's an exponentially thinner n=2 and n=3 and so on and so forth. And I think George told me he checked up to n=6, but then you have to keep track of exponentially small. So this seems to, we understand this analytically. It's confirmed by simulations, but we want to actually test this in the real world. And there's been some questions already yesterday about, wait, haven't we observed this or what's going on? And Luciano described a little bit this technique that we use to image black holes called VLBI. So we don't see black holes the way you and I are looking at each other now, or the way our cell phones take images. We're not directly seeing the image of the black hole. We're seeing the Fourier transform of the image. But the point I want to make here is that I'm showing two images that are the same, that have the same underlying accretion flow onto the black hole. In the top image, I'm only ray tracing the n equals 0 image. So I'm only showing you the direct image of the source. And in the bottom image, I'm including the strongly lensed photons that orbit multiple times around the black hole. And so that adds the photon ring stamp. And the key point is that in the Fourier transform of these images, it turns out that a ring produces a ringing signature in the Fourier transform. So that's the interferometric ringing signature. And this ringing has a periodicity that is set by the diameter of the ring. But if you have a very thick ring, then the signal decays exponentially fast. And the thinner the ring gets, the more long-lived the signal is. And so the x-axis here is the baseline, which for all you need to know for the purpose of this talk is that the baseline that you get to probe with your interferometer is the distance between your telescopes measured in units of the observation wavelength. So it's a dimensionless quantity. And so the way you move outwards to the right is by either increasing the frequency of your observations, which is very hard to do because of water vapor, like Luciano mentioned yesterday. So at fixed frequency, really the only other way that's left for you to go to the right is to increase the telescope separation. And on this plot, the diameter of the Earth is about 12 gigalambda. So you see up to here. And so the point I want to make is that if you're only seeing this first dip or null, you can't tell apart the stick ring with no photon ring on top from this image in which there is a photon ring. And so that's the sense in which we have not yet resolved the photon ring with current EHT observations. In other words, by just looking all the way up to here, you can't tell apart these two things, and you can't demonstrate that this is really what the source looks like and rule this out. So clearly, in order to tell the difference, you just have to go farther out, and you really want to go up to here, where now, because this is a log plot, there would be a huge difference between this decayed signal and this still strong ringing. And so that's about 3 Earth diameters. And that's exactly what we want to do. So there's a huge ongoing effort now. Millions of dollars have been poured into this. At this point, there's over 100 people that are working full-time on this to develop the Black Hole Explorer, which is a proposed NASA mission that will launch a satellite into Earth orbit and connect with the Event Horizon Telescope's ground array, but adding this baseline to space that will give us the added length to probe these longer baselines that will enable us to resolve the photon ring and measure its size, shape, and detailed properties. So this experiment, which we're going to propose to NASA in June of next year, if selected, would actually launch in 2031 and operate for 3 years. So it feels like far away, but this is a chance to actually probe this physics within the next 10 years, which I think is hugely exciting. And an experiment like this would actually allow us to achieve the highest angular resolution ever, take the sharpest images in the history of astronomy. It would let us resolve the photon rings around M87 and Sagittarius star, and also allow us to resolve the shadows, so get blurry images of about 20 other sources, depending on how much time we have on sky. It's expensive. And one of the key targets is to measure the black hole mass and spin for M87 and Sagittarius star. Spin is very hard to measure via other means, but because the photon ring is a probe of the space-time geometry, we think we can achieve this. And if you're interested in how to do this, it's complicated, but I'm happy to tell you more details. And then finally, we'd also be able to look at the jets of many sources and connect what we see on large length scales to the base of the jet and the near horizon behavior, and using polarization images, which tell us about the magnetic field, we think we'd be able to test whether the jet extracts electromagnetic energy from the black hole spin, like the Blandford-Nyack mechanism predicts. That's a very old problem. What powers astrophysical jets? It's been around for 60 years now, and I think it's very exciting that in the next 10 years, we could have an experiment that not only probes space-time geometry at the edge of the universe, which is the event horizon, but also lets us learn about this old mystery of what powers astrophysical jets. Okay, so in my last couple of slides, this is what we can do with the HT. And this is a simulated reconstruction with BHEX, where we have this satellite in space that connects to the ground array on Earth. And if this were the ground truth from a simulation, this is how well we do. So, it's about a 5x improvement in resolution, which doesn't meet Luciano's ambitious 10x goal. So, it's not a perfect image, but it's much better than this, and it's enough to be able to conclude that there's a photon ring on top of the accretion flow. That's what we're gunning for. And we've had now numerous meetings, including one in NASA Goddard, where we got to see the kind of, this is a dish that actually flew in space. That's just like the radio antenna that we're going to use. So all this technology exists pretty much off the shelf. So we're very hopeful that we're going to be able to do this. Okay, and then in my last minute, I want to make a final point, which is a little bit more technical. But you see, I've called this the photon ring, but I've only talked to you about null geodesics. So there's nothing special about the spin 1 nature of light. And in fact, you could ask, how does this connect to gravitational waves, which is another important topic in this meeting. And so this is the famous first LIGO detection, in which you see this in spiral signal when the black holes are rotating around each other. Then there's the rapid merger, and this exponentially damped ring down when the final black hole settles down to its final state. And I just want to show you this other cool video that is a simulation showing you what happens in space-time during such a black hole merger. So you see that there's these two black holes orbiting each other. The space-time metric has these ripples that produce this rippling pattern around the black hole. And now as the black holes orbit each other, at some point they're going to suddenly coalesce and merge into a single black hole. And when that happens, I want you to look around. The last ripples of space-time that you see go around a ring. And this is no coincidence. So this talk was called the photon ring, but it could have been called the graviton ring, because all I've talked about are null geodesics. And in fact, it's well known that in the Eikonal limit, the geometric optics approximation, which many of you have talked about, you can think of a high frequency wave as a congruence of null geodesics. And it was understood by Ferrari and Machoun in the 80s and proved more rigorously by Ayer and Wald in the 90s that for a Schwarzschild black hole, the quasi-normal mode ring down is controlled by the photon sphere. And unfortunately, their analysis didn't apply to a rotating curve black hole, but there was a Caltech group in 2012 that actually did the analysis rigorously and showed that the same story works. And it's possible to obtain an Eikonal approximation for the spectrum of quasi-normal modes entirely in terms of the photon ring parameters. So the quasi-normal modes are labeled by L, M, and N. N is the overtone number, and L and M are spherical harmonic numbers. And so if you want the spectrum, the characteristic frequencies of the black hole, at least when the angular momentum or equivalently the energy is high, so this is the Eikonal limit, you can obtain this analytic approximation. So there's a divergent order L piece and a subleading order constant piece, and then there's sub-subleading corrections that are suppressed in 1 over L, so we don't care about them. The overtone number enters only through this imaginary part that introduces the damping. So as n increases, the overtone number, these modes get more and more damped, so they decay faster and faster, which is the expected behavior. And then all you care about are the coefficients of the real part and of the imaginary part. And if you take a particular L and M, the way you can compute these frequencies is that the ratio M over L, remember M goes from minus L to plus L. So M over L is between -1 and +1. And in the limit where L gets large, M over L becomes a continuous parameter between -1 and 1. And so if you give me an L, M, and N, and you want to ask me to compute what is the quasi-normal mode frequency, all I do is I take M over L. That gives me some number between -1 and 1. And I find the orbital radius in the photon shell for which the sign inclination I introduced at the start is equal to that value. So, basically how much the photon oscillates is directly linked to this M over L. And then the real part of the quasi-normal mode frequency is just the angular velocity of the photon bound at that corresponding radius in the shell. And then the imaginary part, which controls the decay rate, is just the ratio of this Lyapunov exponent that I defined divided by the orbital period. So I think it's very cool that this kind of experiment that we're envisioning will give us a window into strong gravity through electromagnetic emissions, and that the physics that it's going to probe is actually very closely connected to the physics of gravitational waves, albeit in the large L regime that is kind of complementary to what LIGO and LISA are going to see. LIGO can see the L equals 2 modes, LISA will see L equals 3, and this approximation is already good at to the level of 10% accuracy for L equals 3 and is basically perfect for L equals 4. Okay, so I threw a lot of stuff at you. I'm here for the rest of the week. Thank you for listening, and I'm happy to chat more about anything. Thank you.